We have Kunilovskaia from Saarland University, who is also speaking on behalf of Christina Forlì and Heike from the University of Material Design. Sorry for my Polish accent. Good stuff, right? This one? This one, right? Yes. Also? Yeah. There you go.
Could you collapse the bar? The annoying bar, I guess.
Yeah.
Yes.
I have done that. And this one, please. This one.
Works. Okay, yeah. My name is Maria Kunilovskaia, and currently I'm a postdoc at the University of Saarland with Language Science and Technology Group on the LKH. And this my position is funded by this project, which is information density and in language encoding. And I'm interested in my work is focused on cross-lingual modeling and information theoretical indices of information density measuring. Originally, my educational and professional background is in translation studies and contrastive linguistics. Before I assumed my current role, I was an assistant professor in a Russian university teaching in translation studies and corpus linguistics. And then I downshifted to take a PhD position, which I have completed now in the UK. And now I'm again an early career researcher. I'm very happy about that. Right. My research interests are mostly focused on translation inequality in human and machine translation. And this is the first time I publicly venture into interpreting studies, and also have a small disclaimer about the abstract, which was already pointed out. It mentions support vector machines as my method, modeling method, and I decided against reporting these results in favor of generalized linear models now. So there's no support. We have results on support vector machines, which are well aligned with the current results that I'm presenting. As I was teaching professional translation, I did work as a freelance translator and consecutive interpreter, because when you're teaching, you're supposed to be in the field yourself a bit. And I had a month of intensive training in simultaneous interpreting, although it shows that I'm not probably made for multitasking and all that thing. And we have on the team a professional acting acting interpreter who is a sanity check on our results and our methods and that. So my structure is that I'm following a very traditional structure. We're starting with motivation and aims, methodology and results. And the study is about explaining disfluences. Also, there's a question mark in the abstract title, which was not intended, but a research question like what explains what are the predictors of disfluences as the manifestation of cognitive load. And we are going to, while identifying these predictors, we focus on comparing three models, actually two types of predictors and then a full model which combines predictors from from both models. And then we compare also individual predictors, which of the predictors are more explanatory. And our two major approaches is corpus-based features that are traditionally used, including in a series of Ghent studies, which are used to capture frequency of disfluences, Philaes, and information theoretical indices from large language models. My special interest was in comparing target language measures, predictors, target language features to source language features, and whether we are using machine translation models and cross-lingual model, machine translation model, and GPT as a monolingual model. And I wanted to see which of the two approaches are more related to disfluences, to cognitive load. And also another thing is how they're it's not only about how indices from large language models related to the frequency of disfluences, but also their relation between them too. It was shown that in the previous research and theoretically, you would expect a negative correlation between production difficulty captured by machine translation probability and comprehension difficulty captured by target language monolingual model. So the more the hypothesis here, assumption here is that the more effort you invest into producing a text, the easier it is for the audience. That makes sense, right? We'll see what we'll see about that. Our data comes from the EPIC subset for German English, bidirectional subset for German and English, which is annotated, which is which contains manual transcripts from video recordings of European Parliament speeches, and is annotated for 8 types of disfluences. Here is an example of the raw annotated data with this 8 types of disfluences that include truncations, pauses, contractions, stutters, and mid-word breaks, elongations. These prolonged vowels that we have just heard about. The total number of segments, all my analysis is done on segment level. So segment is the number of observations that I have, and it's 2,000, 3,000, let's say 3,000 in each direction. Also, the number of Philaes that I'm showing here is referred to as Philaes +3, because I wanted to downplay the zero inflation effect in the data, and I thought, and Heike said that we probably can include stutters, mid-word breaks, and truncations that I mentioned here at the bottom of the slide, as also predictors of cognitive load, while elongations are, the research group considered that elongations and other contractions are not, first, might not be very reliably annotated in the data, and second, the comments, they're less related to cognitive load than these 4 mentioned here. Okay. The distribution of these 4 types of disfluences is shown here. So the blue is Philaes. So Philaes mostly carry the day. There are more mid-word breaks in German, the green bar, more which is probably also due to the word lengths. But English is more rich in stutters, according to That's my statistics here from this data. Zero inflation still. Roughly 50% of segments, that is 1,500 segments from 300, have zero cognitive load. Nothing's annotated there. Well, the background for this, when we looked for in the literature, it probably can be summarized from what I've seen, that measures of cognitive load. So what do people use as manifestations of cognitive load? So it would be either reading and production time, right? And field pauses, or field pauses, silent pauses. Maybe I do not cover everything, but that was relevant to me. And as for predictors, what do people use to predict that? Mostly, roughly, you can say it's either the corpus-based measures such as delivery rate, lexical density numbers, proper names, or also source language problem triggers, or surprisal from recently from LLMs, and surprisal from corpus also, translation entropy and target text surprisal from estimated from the corpus here in this study. Okay, so our approach, our response variable, as you have, as I've already said, is disfluency counts of the 4 types of disfluencies, and and corpus-based measures that we've used include 12 items. They can be roughly grouped into syntactic complexity and lexical complexity plus delivery rate. So that's 12 indicators that we estimated for source and for target. So which one? Counts of subordinate clues. So they're pretty much traditional, I would say. Tree depths, mean hierarchical distance is probably something that I wanted to highlight here in this list. Mean dependency distance is traditional. Mean hierarchical distance is the length from the head of from the dependent to the head in the syntactic tree. From all these, most of these metrics were estimated based on stanza annotation. So that's that. And here in the lexical group, I can look here, right? In the lexical group, we use the pronouns, but we only use the counts of unique pronouns, not every occurrence, but unique. So on the assumption that when an interpreter have heard this proper name, it's not a problem anymore. Its subsequent occurrence is not problematic anymore, probably. I had a question for one of the speakers about proper names here too, whether it's occurrences or unique types. Then that corpus-based approach is running against surprisal from LLMs. We use the language-specific models or translation direction-specific models to obtain our estimates, and they were and our major estimate is average segment surprisal, which is the average, which is an average across all words in the segment. Also, by words we mean word tokens, stanza word tokens, rather than sub tokens, which is output by language models. Then we also compared out of the shelf models versus domain adapted models that's fine-tuned on European Parliament speeches. And this slide shows already the results, shows that fine-tuned models based on Shannon perplexity on subwords, not on words, but on subwords. Blue bars are lower, indicating that our domain adapted models are better predictors of the next word than the off-the-shelf unadapted, like out of the box models. That's why we well, I will show the comparison between the performance of the two, but most of the experiments are that. So there's a train parameter. Also for training, you might think that it's this good performance can be attributed to data leakage, but I carefully trained on 1,050 segments that did not have cognitive load annotated in them, and then tested on the unseen data with annotations. Naturally, all these annotations were taken out from the segment when we estimated our predictors. This is the general overview of our three models that we compare. There's corpus-based, corpus features that count to 24. On source and target, they are 12, but multiplied for source and target is 24. Then average surprisal here, plus blue score. We throw it in for a good measure. And also word per minute was added into both models, because you cannot say whether it's truly corpus, it's not really corpus-based, right? And full model includes everything. Modeling setup. So instead of support vector machines, we went with generalized linear model, negative binomial type, due to over dispersion, zero inflation in our disfluency counts. It is we used target segment lengths log transformed as an offset, because all our estimates are counts, raw counts. Estimated dispersion parameter from the data. Dispersion parameter was estimated as shown here in formulas, variance over mean -1. All predictors were centered and standardized, that transformed. And the results I will be reporting is on selected features. We threw out everything that was not significant. So we compared models on significant predictors only. I implemented that in Python rather than R. And one downside of this is that this stats model doesn't allow mixed effects, this random intercept. Well, at least I didn't find how to do that. What did we use as our evaluation metrics? For model comparison, we use this range of indicators. Pseudo R squared for fit quality. So I'm still firmly with the validity. I'm that man from earlier today, is like validity and prediction over description. So that I have 4 indicators of predictive power, association trend, prediction error, fit versus complexity. And for predictor evaluations, for comparing predictors, we use effect size, coefficient, and p-value significance. So the results. These are results on the pre-trained models, on the off-the-shelf ones. As you can see, full models are the best. I have highlighted the best performance on all model evaluation metrics, except maybe here, Spearman correlation rank correlation coefficient looks better for corpus measures than for surprisal or for full model. Full model is not even better than just corpus measures, right? But as you see, the predictive power of this model is very limited, shall we say. We explained less than 2% of the variance in the data with any of the models, which raises a question whether we have weak signal or noise, or we are not fitting speaker ID, which should be might have some. But okay, then if we go to domain adapted models, most of our estimates for full model, so that the surprisal based models and full models, due to inclusion into them of surprisal, get better. And now we firmly have now we have competing surprisal model and full model, which probably means the same numbers here, almost same numbers here, same here. The probably is no statistical difference here, which hints already that's probably corpus-based measures did not contribute much, at least in English. Significant predictors. So which predictors were selected from the full model? And they're here ordered by importance based on coefficient. Yes. So for corpus-based model, model with corpus-based features, we have a strong, the strongest predictor is target word per minute. Also here, for both languages, I think target word per minute. Then for English, for both languages, mean dependency distance on the source text. So syntactic complexity, but not hierarchical distance, but comprehension complexity of the source is a strong feature, relatively strong, if you can say apply this description to very weak predicted generally. Then what else showed target multi-word expressions, the counts of target multi-word expressions, target multi-words, this source multi-word expressions here in German. And for German, there are more features included into the full model, and proper names were among the selected indicators. Proper names in the source text, right? Not in, well, probably the same, right? So for surprisal based models, all features are selected as important. And for full model, for English, full model is exactly the same as surprisal based model. So for English, you don't need any corpus measures to get the best results on this data. For German, well, for German, source language here, source language dependency distance, and source language multi-word expressions, and source language proper names seem to be important, seem to be contributing, get some important contributions. And this is the scale of the contributions. Yeah, for I've already named this this is from the full model, ordered again in the order of importance based on coefficient. We can see that blue score emerged as a very strong predictor, and it's a negative predictor, as you would expect. The higher the quality of the interpreting, the lower the cognitive load, right? A bit counterintuitive. Source multi-word expressions from level of formality should have helped, but it didn't. The higher the formality, the more difficult, the more loaded, the more cognitive loaded it looks like this, right? Because it's positive, it's not negative. I would expect it to be negative. Proper names also are positive instead of being negative, but maybe, yeah, these are unique proper names. So, and this, the third question, the third focus of this study is production comprehension effort relation. As I already said, you would expect a negative correlation, and Lin and co-authors, this is a quote from their paper from last year, and they actually find a significant, very small, but negative significant correlation between production and and the comprehension effort. So if we assume that target language or machine translation model captures production effort and GPT captures comprehension effort, and then the correlation should be negative. In our study, you can see from the graphs, I don't even comment on that, regardless of what I did, word level, segment level, pre-trained, domain adapted models, it's all the same. It's very strong, and it's also very strong correlation, like it's confusingly strong. So especially for domain adapted models. So it looks like the more effort the interpreters invest, the harder it is for the audience. Quite counterintuitive. And I spent a lot of time on this study, a lot. And I could not get it to get a negative correlation. So I'm reporting what I've seen, right? I tried to put the data into compliance, but it didn't. It did not yield. So what we have found, the predictive power of all models is very limited. Target delivery rate is unexpectedly more important than source delivery rate. Source dependency distance is important and as expected. And then corpus, other important corpus features such as count of multi-word expressions, proper names, return questionable results, I would say, questionable direction of relation to what's expected. With LLM indices, fine-tuning, adapting to domain helps. And I expected machine translation indices to be stronger predictors, and it was only true for German, not for English. For English, source language surprisal, source surprisal was more important. Blue score, quite unexpectedly, I didn't expect that. Just threw it in for a good measure, and it was included number 2 in everywhere. And no expected trade-off between production and comprehension, despite a lot of effort. Thank you. That would be all for my study today.
Thank you very much, Maria. And questions from the audience?
Production and comprehension effort.
Yeah, I would need the last slide, actually.
Sorry. Slide.
Yeah.
We can bring it back.
Yeah. If you need to, okay. If you need to share it with the people on Zoom.
Yeah, you're not sharing.
Yeah. Then
Okay. So I'm Martha Kaiser-Fierschner from Scotland, and I'm really excited about the study. Yeah, it would be good if I had the slide, but I'll try to do without it. My guess, I don't really exactly know how these LLM derived instances work, but I kind of have a hint that they might work based on n-gram. And blue score is also based on n-grams. Maybe that's why it is a relevant feature. Or maybe that this is just those can do with it whatever.
I don't think I don't think there's a connection between these things, because large language models look at way bigger context than blue score. Blue score is 4 n-grams usually, right? 4 gram.
But it otherwise sucks for anything.
Yeah.
Any kind of evaluation of NT, right? I think this is probably the only context in which it's.
Blue score shows how well the model has guessed the words in the gold in the ground truth, right? That's that.
I don't know.
I'm not sure. Yeah,
Just
not sure.
food for thought.
Yeah. If we accept blue score as a valid measure of translation quality, then but is it? Yes. Yeah.
And another question, because you said that with the model that you used in Python, you couldn't fit the random structure. So why didn't you use R when there is a package that can do that?
Yeah, well, I tried. I'm not an R person. I have some basic understanding of R, so I cannot do, my colleague Christina can probably do that. And actually she did, but I struggle with using the results that I have notched myself. So I went with that, and we've just finished a study on predicting individual feelings from the context speeches, like next word surprisal and previous word surprisal, and it showed that the speaker ID was relevant there, while document ID was not. So she fit both as random intercept, and it did have the relevance there. So yeah, we'll probably look into that. Yeah, so there's a Python library that is a wrap around R, but I was not able to run it in a very small time span that I had, because I decided against going with support vector machines and reproduce it in another message. So it was
Usually
suboptimal.
because these are interpreting corpora, right?
Uh-huh.
So the individual variation usually comes as very relevant and does add to the predictive power of the model. So it would be maybe worth running.
Yeah, we will do that definitely. I will do that before we publish this. We will of course do that, right? And also I thought maybe the truncations were not really reliably extracted, so we will go with just fillers. It would increase our left skew in the data, but maybe that would be a cleaner approach if we use only fillers and notice not elongations and stutters and all that. But because they had this rich annotation, I felt it's being not used to full of its potential, and
I'll try to follow these results if we'll proceed. Thank you very much.
There's another question.
I was just wondering why you were so surprised to see that target delivery rate shows up as a predictor, as one of the most important predictors for this fluency.
over source delivery rate.
I mean, the fluencies are a target production problem. The faster you have to produce language, the faster you have to plan language. And at some point, I suspect that there is a threshold that you can't plan it before you speak it.
Mm-hmm.
Which then induces the discourse.
Well, I kind of expected source language predictors to be more powerful than target language, and
there's very old research that shows that we are actually capable of even coping with as comprehenders, right? As listeners, that we are able to cope with 500 words per minute and still understand what speaker says. No one of us is capable of producing 500 words per minute.
All right.
So I guess that what shows up in the data is just that.
What do you think about multi-word expressions? Multi-word expressions, they should, the more multi-word expressions are there in the source, the lower the cognitive, there should be a negative correlation, the lower the cognitive load, right? Based on your own studies.
Yes, which also depends on how dispersed they are. I mean, how frequent are your what was your cutoff?
Okay.
What was your cutoff?
Yeah.
In this case.
So it can be a technical problem. So we did not extract what is relevant, right? Or I don't remember what's cutoff.
Yeah,
maybe. Nowhere.
Because in our study we put out 4.
Okay.
To have a minimum of 4 same multi-word expressions in order to include.
Okay, I'll look into that.
Yeah,
maybe
that helps as well, because a multi-word expression that only occurs once will not trigger the same facility, let's say, as a multi-word expression that you will have 10 times the same speech first.
Okay, makes sense. Yeah, thank you.
Okay, thank you, Maria. Thank you again.